My name is Eric Larson. I am on the Altair Global Academic team, and I am the manager of our global academic training and the technical specialist for Inspire. And I have been asked to provide this webinar about utilizing Inspire for the contest. We ran our contest last year, had tremendous success with that. Wanted to continue on this year, though we have had we did do a slight tweak to it and made it more robotics oriented. And so to accommodate that, what we've decided to do is create 3 webinars this year. The first one being Inspire. Each of these is designed to give you ideas about how these particular softwares can assist you in the entering of our contest, where you would be asked to improve a robot somehow. That can be through traditional light weighting of the robot to improve its performance. It can be through using our AI Studio software to use data to improve maybe the reliability or the function of your robot, or PSIM to improve the electromechanics of your robot. And these webinars, while they are not complete trainings, are designed to provide you information about how you could utilize these particular softwares. So this is our Global Student Contest page here. All the information you could want to enter the contest, to get the software, to learn the software, can be found on this page here, including submitting your entries. And we would encourage you to get on submitting your entries as soon as you can. If you're not ready yet, there is an option in there to be reminded about submitting your entries as well, saying you're not ready yet, but send me a reminder, just to keep you aware that we're still going strong here. We will be awarding the first quarter's prizes sometime in January, and hope to see your entries. So Inspire. You may or may not be familiar with Inspire. Inspire is an analysis tool. It's a light weighting optimization tool and a motion analysis tool. And all of these can be combined such that you can use motion to drive analysis or optimization, use analysis to drive optimization. Really kind of an all-in-one package for improving the mechanical systems of your robot, part design, assembly design, that sort of stuff. This page here, the Altair Inspire Academic Hub, is kind of the central location for acquiring the software. We've got specific modules in here to help you quickly learn the software. So I'll be demonstrating some of these features here. This is where you're going to want to go to truly learn Inspire. And we cover the basics, structural connections, optimization, motion, and utilizing motion to drive structural analysis and optimization. You can do other things from here as well, finding some additional trainings that we have. You can get certified in Inspire, and there's material for professors on there as well. Because this contest is robotics oriented, I also want to talk to you about our Altair support for FIRST Robotics. This website has a tremendous amount of information about our support for FIRST Robotics. Well, the vast majority of our entrants in last year's contest were of the university level. We have opened it up to all ages, so high school students or even below that are welcome to enter. And we would love to see what you can do with your robotics optimizations and improvements. So like I said, well, we're not going to go into a full-blown training. I do want to introduce you to the main things that you can do with Inspire to improve a robot. And the first of which would be really a simple structural analysis. So if I want to analyze a part, I can bring geometry in, and we do support the opening of all forms of geometry, no matter what CAD system you're using. We can support it in its native format, as well as the intermediate formats like Parasolid, Step, IGES. So no matter what format you have your geometry in, we can bring it into Inspire. And Inspire then allows you to very quickly and easily get analysis results. We support multiple materials. When I want to define a material, I just simply need to right-click on a part, and I can select from a library of materials, or I can add my own custom materials. For this, we'll make it aluminum. And then we can very easily and visually create a structural analysis. In fact, we can do it faster than just about any other software out there by simply coming to structure and defining the structural components of this. So if I want to hold this part in place, I can click on my support and click on what I want to support and define the parameters of that, allowing it to, say, rotate or translate in certain directions. I can then come and, so let me change that one as well. I can then come and add loads, pressures, moments very easily up here in this icon. And again, to truly learn the software, please take a look at those modules in the Inspire Academic Hub page, where there are videos that I created where I'm going to go into far more in-depth. Again, this is just kind of to give a overview of the capabilities. So in this case, I'm going to put a force on this hole right here. I'm going to change this to bearing load, and I can even then very easily come and orient that bearing load however I want it to be. So we'll put it right here, and then I can define what the force on that would be. So we'll say 50 pounds force. I can even define secondary loads, so I can come here and say put pressure on that face or a force on that face. We'll say 20 pounds on that face. And then I can even define multiple simulations. So I can come here and say, okay, this load case is going to have my bearing load in it, but not the side force. Or I'm sorry, not this, the bearing load in it, but not the side force. And I can create a secondary one where I use my two supports and I just analyze the side force. And I can create a third one where I utilize my two supports and maybe both forces are occurring at it. So I can create essentially an unlimited number of forces and supports and then pick and choose them, I guess essentially buffet style, to create a multitude of different load cases. So you can analyze all the different instances, all the different scenarios that your particular part may encounter in its utilization, and be able to quickly and easily analyze those. So with all of that defined, really I'm ready to run my analysis. I can click Analyze here. To move this, go to Webinar Control Panel here, and we'll go right there. And everything's set up. I can even do normal modes analysis if I want the frequencies of it. And I can click Run, and now it's going to go through and it's going to very quickly run a structural analysis on this. It will mesh the part based upon calculations that it did on the overall size of the part. Making sure that features are captured, making sure I have enough elements through any small cross-section, and doing everything possible to make sure that I have the most accurate analysis possible. And then I can come here and take a look at my results. I can animate them so I can see how the part behaves. This animation, you can see here, this is an incredibly small amount of deformation. This animation is automatically exaggerated, in this case, by 1,762 times, just so you can get an idea of how the deformation of your part works. Otherwise, if we didn't do that, you wouldn't even be able to see this. It would be so small, and you'd have to scale it up. So we take care of that for you. And that's really what Inspire, one of its strong points, is it kind of knows what you're going to want to do, and it typically takes care of that for you. As a stress engineer, the very first thing I would do is increase the multiplication factor on my deformation so I can see how it behaves. Altair takes care of that automatically. I can take a look at things like stress. You can see there's not a lot of stress on here. Let me reduce this a little bit just so we can see. Well, that's reduced it a little bit too much. Oh, because it was 500, not 50. So we'll try 200. There we go. So now we can see our stresses here. I can take a look at my tension and compression, so I can see, yeah, this side is in compression, this side is in tension. If I'm concerned about the failure of my part, I can check factor of safety, which I'm perfectly fine here, or percent of yield, but can very quickly and easily prepare structural analyses. And based upon this, I find that my part is well beyond its structure. I mean, the part is way over-designed. It is well beyond the force that is going to be applied to this. So I know there's opportunity for optimization on this. And that's Inspire's next strong suit, is the creation of optimized design. Sometimes people have used the term generative design. We call it topological optimization. That it's its true name, and it's something we introduced, oh my, probably 30 some odd years ago to the industry, and have been fine-tuning and improving and acting as the global leader in optimization technology. So what I can do with that then is I want to create an optimization. And if you're not aware of how optimization works, is it takes the part with your forces, with your constraints on there, it does an analysis on there, and then it goes through and determines the contribution of every element to the strength of that part. And if the particular element is not contributing to it, it gets rid of it. So essentially it's like a load path analysis. It's determining how the load progresses through the part, and then making sure it has material there and getting rid of all of the excess material. I often liken it to sculpting. If you're going to carve a sculpture, you take a chunk of material, you determine what material needs to be part of your sculpture and what material is not, and you get rid of the excess material, and you have a beautiful sculpture. This does a similar thing, but determines not based upon beauty, though the parts that it comes up with are pretty cool looking, but based upon the necessity of that element to the contribution of, or contribute the contribution of that element to the overall strength and behavior of the part. So it carves away the material that's not necessary. But of course, there are some features on here that are necessary, these mounting holes, for instance. And I can very easily protect those if I simply come back to my geometry ribbon here. And I come to this tool called partition. And I select, say, a hole that I want to protect and give it a size. And now what's happened is you can see this now is its own separate entity. And that means when I define this big chunk of material in the center as design space, which is the material that can be eliminated, the non-design spaces, the parts here that I have protected, will not be touched. So you're guaranteed of always having a mounting location, a loading location, part of the material that's non-negotiable. It has to be there. We define that as non-design space, and we'll be going through how that's done in just a moment here. But we separate our part out, and we can do that very easily through the partition. So again, this is going to be 0.26. And we'll protect this hole here. And we'll make that 0.4. And now I've taken my one part, I've split it into 4 separate parts with the advantage now that I can right-click on this big middle part, define it as a design space. And you can see now it kind of turns this maroon burgundy-ish color, whereas my non-design spaces have remained their native color, which in this case is gray, though that can be changed to whatever we want it to be. Oops, I hope if I actually selected the proper one. I'll probably grab that one. There we go. So I can make these any color. The gray is just the default. But anything that you see that is not changed into this kind of burgundy-ish looking part is non-design space, and the design space is what can be carved away. I then would add my loads and constraints on here again. I would come, and if I come to my structure where I would add my loads and constraints, I can add shape controls to this. I can add symmetry if I want to make sure that my part is symmetrical across one or multiple planes. I can define manufacturing constraints. So if we come here, you can see we've got single draw, split draw, extrusion, overhang, milling. Single draw and split draw guarantee that a part won't have cutouts in an orientation that you can't have them, say if you're going to be casting it, or holes in the wrong location. Extrusion, which is what I'm going to use on this part, what it actually does is it guarantees that my part has a constant cross-section, thus guaranteeing that I could do a water jet cutting on this or a laser cutting. It makes sure that I have a constant cross-section. Overhang is typically used on 3D printed parts, where we know, or know if you're familiarity with 3D printing, additive manufacturing, that you can't print something hanging over nothing. So there is a maximum angle at which you can print the next layer up. And utilizing this will guarantee that your part maintains specific overhang angles, which means that you don't have to create supports for it. And then finally, milling allows you to determine 5-axis milling constraints to guarantee that your part is millable on a 5-axis machine. And then from there, I can just simply go to my optimization. And in my optimization panel here, I have 2 objectives. So the objective of an optimization is obviously to lightweight the part. But how I go about doing that, we've got 2 main ways of doing that. The first of which, and the default, is maximize stiffness. Maximize stiffness, you tell it how much of the material can remain. The default being here 30. And what it will do is it will get rid of 70% of your design space. So 70% of the design volume will be removed, leaving the 30% that I specified here. But it will do so to make sure that your remaining 30% is distributed in a way to make the part as stiff, as resistant to deformation as possible. Your other choice here is minimize mass. What minimize mass does is it looks to get rid of as much material as possible. Of course, that would, with left unconstrained, it would just get rid of all the material. So what I utilize here is a stress constraint. So this optimization technique actually takes stress into account. The previous one was focusing on stiffness. This is focusing on stress. And what I can do is define a stress safety factor. So in your material definition, I'll come back to the optimization here. In your material definitions, there is a yield stress in the material, whether I've entered my own material or you're utilizing the material library, there's a yield stress in here, and that's what we would consider the failure of the part if it were to yield. So it will take that yield stress, it will divide it by whatever your safety factor is, and set that as a stress limit, so that as it begins to remove material and the stress begins to rise on your part, it will be constantly checking that stress and making sure that at no point does the stress exceed the safety factor stress that you've set. And if it does, it'll move on to different areas and get rid of as much material as it possibly can while making sure that you don't exceed your stress safety factor. If vibration, if frequency is a concern to you, you can actually put frequency constraints on here. Thickness constraints can be added to dictate how thin or thick any of the remaining structural members can be. And then I would click run, and if I come here, this one right here, so you can see we set it up in the same way. What we can do now, unlike the structural analysis that I kind of did live here, this one would take a little while. It'd probably take about 4, 5, 6, 7 minutes to run, and obviously we don't want to waste the time doing that. So I've pre-run this, and what we can then do is take a look at what the part would look like if I had that optimization run. And you can see it's gone and it's gotten rid of materials, but it's done so in a logical manner to make sure that my part is either as stiff or stress resistant as possible, but getting rid of as much of the material as possible otherwise, and leaving you with a design that are in many cases not intuitive, because we as engineers can't look inside the part and trace the exact path of the material, or of the load. The optimization algorithms can do that, and it will come up with a truly optimized design. And from here, all I need to do is come here and click this Fit Polynerbs. And what it will then do, let's turn that off and show you what the Fit Polynerbs looks like, and it will create this very nice smoothed geometry. So now this is more along the lines of a part that I truly would want. And now I can take this back into my CAD system. I can make any changes necessary to it, or quite honestly, I could not even go to the CAD system, come here, save it as an STL file, and send it straight to my favorite slicer, and 3D print this in whatever material you want to do. And along those lines, if you are looking to do 3D printing, we do have defined in our library already plastic ABS and plastic nylon, or you can utilize the material specifications for whatever you're looking to 3D print with. Of lightweight parts is very easy within Inspire. You saw how quickly I could set up the analysis. From there, it was really just a matter of setting a few optimization parameters, establishing my design and non-design spaces, and from start to finish, from bringing this geometry in, I could have an initial analysis run. I could set up my optimization, and within, say, 20 minutes, I could have an optimized design that's CAD or production ready. Some examples of how this has been used, if you watch some of these videos here on the Inspire, the first page, Colin Dagg from the HOT team will go through and he describes optimizations that he did with Inspire to improve their robot design. And I think we've got other use cases in there. But you can take a look and see how other people are utilizing optimization within Inspire to drive their designs. So I don't know. I guess we do have a chat here. If you have any questions, please don't hesitate to drop them in the chat. I'd be happy to answer them. Or if you have any other questions on the student contest site, I believe we've got a link somewhere on here to the Altair community page where you can go through and let's see here, somewhere on here. Now, I won't waste our time. Somewhere on here, we've got a link to our Altair community page where you can ask questions after the webinar is done or anytime through the contest to receive assistance in preparing your models and your submissions. So we've covered briefly, albeit, and again, please take a look at the website for actual training material. Each one of them is relatively short, but that will actually get you going with it. And there are models that you can download and you can work with them as well. But now what I want to do is I want to tackle one of the more advanced capabilities of Inspire, and that is the motion analysis capability of Inspire. And so what motion analysis allows me to do is bring in geometry. So we've got this intake here. I think this was a first robot intake from a couple of years ago when you were picking up balls or something like that. And this is all the geometry. And I want to make this move. I want to see how this moves if I put a particular motor on here and I establish the joints between all of the connections here. And I want to make sure that I designed these such that it will move properly. And we can do that through our motion analysis here. And the way that we go about defining the motion capabilities of our particular design is we typically start here on the left and we work our way across. And the first thing that we're going to want to do is establish a ground. And the reason we want to establish a ground is because if I come here, let me just analyze this for 1 second here. If I come here and I quickly run the motion analysis, you're going to see, oh, it just falls. Well, the reason it's falling is because if I come here and take a look at gravity, gravity is pointing down. So this is doing the motion that it would do, which is just fall down because gravity. So what grounding does is it holds something in place. Something has to be held still such that all of the other parts, assemblies, features within within your design can move relative to it. So if I come here to my ground, I can establish my ground, and I'll pick these two panels right here. And what I typically do in this case is I do a step and I do a quick analysis to see if that worked the way I wanted. So I click Analyze again, and you can see it worked, but I seem to have missed a few pieces here. You can see these little support members here. And the attachment members are falling as well. So I can just come back to my ground and maybe zoom in here. And had I zoomed in, I would have seen them here. So they're still staying in gray. So I'll pick all these. And then analyze my part again. And now what I'm holding in place is staying in place. And what I want to do from here is work my way out. I want to establish how this part, how every other part is connected relative to the ground. And I do that through joints. And if I come here and I click Find Joints, it's going to take a couple of seconds. It's going to look at all of the geometry, look at the configuration of the geometry and its proximity, and it's going to determine regions where a joint might exist, and it's going to color them red. And I can see here what it's done is, let me get out of here for a second, this tube, which is attached to this first arm here, runs through a hole in my ground. And so it has determined that at this location here, because it's a tube running through a hole, it's likely to be a place for a joint. So I can click on that. It's going to turn into this shape right here, and it's going to call it cylindrical. And we have a number of different joint types. I won't go in depth into all of them, but I will say in this case, cylindrical, what it does is it allows rotation, but it also allows translation along the axis, which I don't want. So I'm going to change this to a hinge. And what hinge will do is it will allow it to rotate around the common axis between the circular tube and the hole that it's going through. And I'll click this one as well and change that to hinge. And now when I leave here, there's nothing shown on here after I leave the joint, but you'll notice now if I come to analyze my motion, in fact, let's bump that up to 2 seconds, and I click run, that now, let me move this out of the way, that now is rotating. It's doing what I would expect it to do. If I held this in place and I allowed this to freely rotate around that hole, this would swing back and forth. You see it's passing through these parts here because I have not defined an interaction between them. So it's ignoring any potential interaction, but now it's allowing it to freely swing. And what I now do is just come from part to part and define my connections. So I can come here back again to joints, find my joints, find again that this is now running through here. So I'll click that. And I want that to be a hinge, and I'll click that, and I want that to be a, oh, not grounded pin. Let's undo that. And we do have a handy undo button right here. I'd probably click the wrong thing, but that's fine. That one hinge will actually work. And now if I come here and I take and look at analyze my motion, you'll see now we get a real wild design because I got two things connected to each other, and I progress through and I continue that through each one of the different joints that I have, combine things together. In the case of this right here where I have these two brackets that are connecting these two, actually let me create my joint first here. So let me find them again, and we'll grab that right there, and that's a hinge joint, which would mean that that's going to stay connected, but everything else leaves. What's holding these two things together are these two brackets here, and I could go through and define connections between them, define joints and lock them. But in this case, the easiest thing to do, since this arm, these two brackets, and this arm right here will always act together, I can define them as what we call a rigid group, where this, and this will always act together. They can't move relative to each other. So now when I analyze my part, you see the rest of that comes along for the ride. Oops. Oh, well, you know, it would help if I actually created it. Even somebody who's been doing this a long time tends to forget things every once in a while. I selected them, but never clicked the little create. So now they go hidden, and now you'll see They're all behaving together. And I would go through and now define all of the rest of these. But we don't need to continue to do the same thing over and over again. What I want to show you now is the ways that we introduce motion. As opposed to just free falling and rotating, we want this to behave somehow. And I do that through motors and actuators. If I want my relationship to turn, I use a motor. If I want my relationship to move linearly, I use an actuator. So this motor here is what I'm going to use. And I'm going to apply it to the center of that hole right there. And now I define how I want that to behave. Right now it's set as a 60 RPM motor. And if I come and I take a look at this motor here, it's set for speed. It's got 60 RPM. And I define the function for this. So how long will this run? And what time will it start at? So a step function is just literally going to step it up. So it's not going to instantly go to 60 RPM. That doesn't happen. So I'm going to say I want this to start at time 0, so that's fine. And I'm going to run it for the full 2 seconds. And if I take a look at this now, I can see this is the profile that it's established for it. So at 0 seconds, it's going to begin to ramp that up. I can actually grab these points and move them. Or if I have a definition of at particular points, it's going to be at this speed, I can actually even import that, convert this to a table, and I can import a CSV file. And bring that data in here. But I'm just going to leave it to control. And now you'll see if I analyze my motion, you know what, as opposed to having a go with gravity, because that doesn't show anything. Let's reverse this. So I'll have it spin in the opposite direction. And we'll analyze the motion, and you'll see it begins to spin it. So gravity still has an effect on this, but the motor is overcoming the gravity to spin this. I can also set this as a speed, angle, acceleration, torque, and define the behavior of my motor however I want it to be. The other option would be an actuator. An actuator goes from one part to another part, and it's just a linear actuator. And much like the motor, I have to define whether it's a displacement, a velocity, acceleration, or a force actuator, and then define its parameters. It was automatically defined as a step dwell step, which means it's going to start at 0. It's going to take half a second to move its full length. It's going to hang there at that length for a second, and then take a half a second to pull back. I don't have actuators on this because everything is going to be motor driven, but that's how you would define a linear motion. And again, to save you the trouble of seeing this all through, this I should have, did I not? Oh, there it is right here. This has already been predefined with all of the motors. These are angle motors, so they're going to go to a specific angle at a specific time. And if I want to, I can now come here and visualize the motion of this, and you will see. Now let's slow this down just a little bit. There we go. Now we can see. So this motor is rotating it. This motor takes over. This motor is spinning at the same time, and then the motor attached to the intake will begin to spin here in a second, and it will turn that. There it is right there. So we can simulate up of a ball, for instance, by rotating each one of these and making sure. And the cool thing about it is, once I have the motion defined, if I click on any of these motors, it creates a graph for me showing what the torque requirements of that motor is. I defined it as an angle, so I said, okay, at this time, you're going to be at this angle, irrelevant of how much torque it takes, but based upon model, the inertia of all my individual parts. It will require some torque to get there. So I would appropriately define the materials for all of these, and then I can determine torque requirements. And again, all of this is covered in the main classes and the modules, but just a brief overview of that. Now, not only can we just simulate the motion and use it to kind of fine-tune our motors, determine the motors that are necessary, or actuators, or springs for that matter, I can also utilize the data from this. So as this is running, if I come here and select any of my joints, oops, let me come back into, there we go. The force that's acting on this joint throughout the entirety of the run here is being calculated. So that joint, let me get rid of the components of it and just leave the magnitude. That joint is seeing this amount of force acting on it. So through the entirety of the motion, it's calculating forces on that joint. And what I can do then is, once I have a motion analysis, let me come back here, I can click, I want to know the stress on this arm. So I click this, it asks what part I want. I can tell it just look at the 5 peak loads or use all of the time samples that it did, and it will run 302 individual analyses and then string them all together, kind of like a movie. And we can end up with something that looks like this. So this is a different robot arm here. And oh, this is in a different, let me run this. This was in a different version, so it's going to take a little while to retrieve those results. Oh, actually, you know what? It's right up here at the top of the, nope, not this one, Altair Academic Hub. This right here, oh, there it is, right there. So this, you can kind of see, I can't animate it right now. I can see if it, by the end of my discussion, let me try loading them and see if by the end of my discussion they've loaded up. But this was run in a previous version, so it has to convert the loads to the new version. But we can see here, this, I don't know what loads are on these arms here as a result of the inertia of this system. It's utilizing the load, the forces, the loads that it calculated as a result of the motion, and applying that. And throughout the entirety of the motion of this arm, I can now see the stresses that are occurring on that. And so I don't even have to know the forces that are going into my part. So it's actually even a much more accurate analysis on parts that are being assembly, because I don't have to estimate forces, and I can see the effects of that force change and orientation over the entire of that analysis. So I can combine motion and analysis. Last but not least, I can combine motion and optimization. So I've got a slightly different arm here. Oops, not this one. This one right here. We'll get to that other one in a minute. So this is another clamping bracket from a robot. It mounts onto something here. This little actuator pushes these, and these angles will open and close these little jaws. And I want to optimize this part right here. So let me isolate that again. And to do so, I need to create my design space. So what I can do is come through and utilize the tools within Inspire, these simplify tools. I can fill up holes, fill up entire regions here. I'd have, in this case, I would have to go through and select each of these. fill those all in to create that design space and end up with a design space that looks like this. So fill in all those, not utilize the lightweighting holes that were put in arbitrarily, but now develop an optimized part. And then just like I did in my optimization discussion, I established my design and non-design spaces, so I protected all of my mounts here. And then I would go through and set up my motion analysis, establish my actuator, establish my joints, and run a motion analysis on this. So I'd go and run the motion analysis, and now as opposed to clicking Analyze Part, I click Optimize Part, and whatever design space is on here, and you can see the optimized part, no motion analyses are found. And come back to here. If I come to the optimized part, it'll help if I have a design space, so let's just make a design space. The options in here are exactly the same as the options I had in the in just the straight static optimization. And I can now end up with an optimized part that looks like this. And again, by using the polyNURBs, I can get a nice smooth shape. And then I can come to my Analyze. Oh, and these were done in a previous version. Hopefully these will. I can come to my Analyze, and I can see that that analysis on this part as well. So in short, Inspire can do just about anything you want to do to structurally analyze your part, to optimize your part, to evaluate the motion, and then even combine the motion with analysis and optimization and determine your best shape, your best design, your best, most lightweight motion analysis, multi-body system to make sure that you have optimized and improved your robot. And again, oh, there we go. That was quicker than the other one. So you can see what I did is I added this tube in here and then created a contact between the gripper. I didn't cover contacts in the motion because that requires a little bit more. Between the gripper and the tube. And now I can see when this grabs onto the tube, drop this down just a touch. What sort of stresses I see as a result of this. Oh, that's way too much. That's better. So I can see the stresses that occur as this begins to grab onto this tube. And so I've combined my motion, my optimization, and then structural analysis to determine the behavior of my new part here. And once you have that, just create a 5-minute video on it. Put it on YouTube or Belly or whatever video system, video sharing system you want. Send us the link to it in the submission, and we'll take a look at it and evaluate it for our 3 quarterly contests. So each submission is valid for the quarter that it was entered into, and would be evaluated against all of the other ones, and we'll be awarding 3 top prizes. I think they're outlined on our contest here. Where we're somewhere on here. It says the prizes. There they are. First prize, $2,000. Second prize, $1,000. And third prize, $500 for every quarter. Plus, if you are a first team member, you can create a short 60-second video talking about how you would like to use Altair products on your first team and why we should consider you for a $5,000 sponsorships. And over the course of the 9 months that this contest is active, we'll be awarding 3 of those. If you are in college, you have the option of doing something similar, a 60-second video talking about how you'd like to utilize any of our Altair products and share that with your fellow students and become an Altair ambassador, where we will pay you up to $1,000 based upon your interactions and the things that you can do at your university, talking about the Altair software. So we have a number of different ways to earn money off of this contest, and we'd love to see your submissions. Absolutely get them in as quickly as possible to be considered. The closing time for the first quarterly contest is midnight or 11:59 and 59 seconds of December 31st, and then sometime in January we'll be evaluating those entries and issuing out the awards. And we very much look forward to seeing your submissions in the near future. As mentioned before, if you're looking to use Inspire, go to the Academic Hub. It's just web.altair.com, academic-hub-inspire, and get your hands on these modules, learn the software, and then take what we've talked about and get to work on it. If you, also worth mentioning, if you don't have geometry, if you're not on a first team and have a robot geometry or whatever, GrabCAD's always a great place to go to take a look at the geometry. But we have supplied a couple of models here. This actually was the kit bot from the First Robotics 2024 season, so full robot model. And then a gripper similar to the one that I was working on here tonight. If you need a little kickstart, don't have your geometry, by all means, get your hands on those and utilize those. We welcome optimization or improvement of any robotic design. And again, it doesn't just have to be structural like we discussed tonight. Take a look at the other webinars. You can take a look at other opportunities for improving your robot design. And one more thing. You can enter, I can't remember whether it's as many times as you want in a quarter. I know at least one per quarter, but you can enter in all the quarters as well. So multiple entries are accepted and encouraged. Take a look at the terms and conditions for how many entries you can do, and look forward to seeing your submission. That's all I got. So again, thank you so much for your time in attending, and take care.